session chair, Dr. B. Viresh. Dr. B. Viresh is Associate Professor in Department of Mathematics at Rao Bahadur Y. Mahabaleshwara Engineering College, Ballari. He holds an MPhil degree and he is currently pursuing his PhD degree from Dharwad University, Andhra Pradesh. He has he has teaching experience of 19 years and his specialization in engineering mathematics, numerical methods, wavelet-based solution for differential and integral equations. He has published over more than 17 research papers in reputed national and international journals and presented papers at various conferences. He is a recipient of Rashtriya Gaurav Award in 2012 and Best Citizen of India Award in 2013. Beyond academics, he has actively contributed to student welfare, sports and social services. With this brief introduction, now I'd like to request Dr. B. Viresh sir to chair the session.
Good afternoon, everybody. Now I introduce Kumbi Narsaya sir to this gathering. Sir has completed his PhD from Karnatak University, Dharwad, under the guidance of Dr. S. C. Shiral Shetty, Professor, Department of Mathematics, and sir has presently working in Bangalore, Assistant Professor in Bangalore University, Bangalore. Sir has published more than 100 national and international papers, and he has presented more than 50 papers in national and international conferences. With this brief introduction, I welcome you, sir, for this session.
Thank you, sir. Am I audible to everyone?
Once again,
am I audible? Hello, am I audible?
Yes, sir, audible.
This is Kumar sir from Bangalore University. So first of all, I would like to thank Shiral Shetty sir for giving me this opportunity to present my research work in international conference held in Karnatak University, Dharwad. This is my title. This is my title. That means wavelet analysis and its application. This is the table of content. First, we shall have some introduction about the wavelets and how to create these wavelets. That means let's move to the abstract. This is my abstract. This talk is aims to present a general way of constructing of orthonormal wavelet basis under the umbrella of Hilbert spaces using the functions by discretizing and also I'm using the continuous function along with their properties in the form of theorems, and how to create operational matrix of integration and little bit numerical applications of a newly generated method using this wavelet. And we have considered one new model, that is a romantic and interpersonal relationship model. By using this wavelet techniques, we solve this model, and we are analyzing some of the parameters, how one family wealthy and healthy, how it affects on our society. So we are going to study by this wavelet technique. Before using this model, let's move to why we switch over to this wavelet methods. Here just introduction about the why we need numerical methods, and then we switch over to the wavelet techniques due to some of the well-known property of the wavelets. If as a mathematician, if we want to study any real life situation, then obviously we won't directly study those real life situations. Instead of that, as a mathematician, we transfer this real world of just a polynomial equation or a system of polynomial equations, sometimes ordinary differential, suppose rate. When times goes on, the problems, issues are the rate goes on vary, then we get differential equation, sometimes system of differential equations, partial differential equations, sometimes fractional. So these methods we can solve in three different ways. The first one, the analytic and semi-analytical and numerical techniques. The first, as we know, the analytical solution is always better than remaining two methods. But some of the times when we model the mathematical, obtained mathematical equations are simple or just linear, then easily we can solve those modeled by the analytical method. But when it is a complex, then you switch over to the semi-analytical method. What semi-analytical method says, it yields infinite series of solution in the form of infinite series. That means when by iteration wise, term wise time, one term, second term, third term, similarly, we get when we get a more number of iterations, we get more number of terms in the infinite series. If the each and every obtained sequence of the solution is in a definite pattern, then we can say we can put in well-designed form. For if suppose, for example, if the first term of the solution is 1 plus second term will be x and third term will be x square by 2 factorial, then obviously I can analyze what will be the fourth term. So by summing of infinite series, we can directly say x, e power x is the solution. If it is not in that manner, when you finding the solution for the any model, if you are not getting a sequential order, then it is very tricky. The procedure will be huge. Then it will become a time consuming technique. So that's why then again analytic to semi-analytic, then again semi-analytic to we switch over to the numerical methods. In numerical methods, we have plenty of methods based on our initial and boundary conditions. We are going to choose the respective numerical methods to solve the respective mathematical models. But here we are opting the wavelet techniques. Why we are using the wavelet techniques? Because why I have given this SIR model means how the model has been generated from the real world situation to mathematical. So this is a simple SIR model. So that means susceptible, infected and recovery. When the times goes on, susceptible and infected recovery goes on changes. To analyze this property of this model, we need to seek the numerical, solutions. Either it is analytical, semi-analytical, numerical. But if it is simple, already I have told you, simple, we can move analytical. If it is a little bit complex, we can move the semi-analytical, or whenever it is time-consuming technique, then we switch over to the this numerical technique. Out of this numerical technique, we are concentrating on wavelet technique. Why we are moving wavelet technique? So for why? So let's have a look on what we mean by wavelets. And generally speaking, the wavelet says it is just a part of the wave. I am not assuming the entire real line system. In the entire real line system, just I am considering the one part with a small domain, which is oscillating in the respective domain, and remaining all except this small domain, in remaining every domain, the function is going to be 0. So that's what in general I can say it is a wavelet. And here different types of wavelets we can consider. So that is the discrete, smooth, compactly supported, and wavelets with simple functions, and wavelet with filter banks, etc. And most simple one is our Haar wavelet. So now actually if you you are in KVD, so that's why you are having you well know the word wavelet, because the Sheryl Shetty specialization is wavelet. If you move out of this Karnataka or somewhere, the wavelet means they seems to be it is a new word. They definitely say it is a new word because this wavelet is not much older subject. It is a recently, in some just 2 decades back, it enhances much more due to its vast applications. Here I am going to constructing the orthonormal basis, which is a representation of wavelet in 2 different criteria I am going to considering here. One is in the Hilbert space I am going to create it, and another one with using the only one simple function and using the 2 operations, scaling and translation, I am going to creating a plenty of wavelet babies which are acts as a basis. And here, before going to definitions, let's one question. If suppose I consider a one Hilbert space, let's say L2R. In the Hilbert space, obviously there is a space means definitely there will be a basis. I am considering a sequence Ek is an orthonormal basis in your Hilbert space. Then obviously we know if any function belongs to the respective space, definitely those functions can be represented as a linear combination of, by linear algebra concept, linear combination of those basis functions. That's what I have represented here. Now I want to represent exactly f by this linear combination, means I should able to know the what is the value of Ck. But it is an infinite sequence. If I move the practically to calculate these Ck, then it is whole my life is not enough to find those coefficients. So because we know when the series, infinite series is going to be converged, whenever its partial sum is converged. That means what? The partial sum, whatever the value yielding, the same thing will converge whenever you converging the sum of the infinite series. So that means I am going to representing the infinite series by the dominating coefficients. That's what the wavelet will do. The same, whatever the concept we use for the series is going to be convergent, same concept here also I will use to say, to represent any function in terms of the approximation of by wavelets by dominating coefficients. So let's move. How I am going to, opting the dominating coefficients, and after 5 to 6 slides you will understand. Let's move what is meant by wavelet mathematical. So this is the mathematical definition of wavelet. If any function belongs to your Hilbert space, j, k belongs to integer, the set of integer, define a function psi j, k by the psi j, k of a function is nothing but 2 power j by 2 psi of 2 power j x minus k. The function psi is called wavelet if this sequence acts as a orthonormal basis for our Hilbert space. So that means any wavelet, any function, if I want to say that is a wavelet, I should generate a infinite number of element containing sequence that should form, that should act as a basis for your Hilbert space. Then only I can say the psi will be a wavelet. It look like a little bit cumbersome, right? So because you see, just one function, with respect to that one function, by operating a scaling and dilation parameter, I need to create an infinite sequence, and that infinite sequence must be acts as a basis, orthonormal basis for your L2 alpha. Then only I can say psi is a wavelet function. Here for my convenient, I choose the dilation parameter as this and tk as a translation parameter. And next I am going to denoting this psi jk as a dj tk psi. So this is a definition. That means I am going to creating a this orthonormal basis. Here the systematic study of the wavelet basis began actually around in 1985. But first example of the wavelet appeared much earlier. That means already in 1910. So was first proved by the Haar, the famous Hungarian mathematician. He has constructed the sequence of psi ijk. So by the Haar wavelet, he proved that it is already orthonormal basis. So by using the above definition, definitely we can accept the psi is going to be the wavelet. So here is the Haar wavelet definition. They are represented as this in the unity interval. For the orthonormality, if it is satisfied, then only I can say, if it is orthonormal basis, then only I can say it is going to be wavelet. Let me check how it is going to be orthonormality. So for that one, I have considered the two functions, let's say psi jk and psi jk prime, the two functions which are generated by the psi of x. Now I take an inner product because orthonormal, I should take inner product. So the as usual procedure, I have considered the orthonormal of these two functions by using the dj and tk, which is an operator on psi. Because dj is unitary. Because the parameter d is going to be unitary, so therefore its power is also always unitary. because in the functions analysis we know what you mean by the unitary. After simplifying, finally it is reduced to the Kronecker delta functions. Whenever k is equal to k prime, then it is 1. If k is not equal to k prime, then it is 0. Kronecker delta function. Next, if suppose I choose, let it be j prime is not equal to j. That means 1 should be either greater or lesser. For without loss of generator, I am going to assume that let it be j prime is greater than j. If I assuming this, again I am considering the inner product of those wavelet function and simplifying, applying the property of this operator, and finally I will get inner product of this. But we know that the Haar wavelet is defined in 0, 1, the unit interval. But this function, whatever this function I have defined, this is going to be its support is going to be this interval. That means after simplifying this interval, finally I will get this is my interval. What is the support of Haar wavelet is 0, 1, and this newly obtained function is support is this. So therefore, the length of this newly obtained interval I is 2 power j prime minus j, which can take the values 2, 4, 8, that means 2 power 1, 2 power 2, 2 power 3, 2 power 4, similarly so on. The length will be 2, 4, 8 and so on. But the Haar wavelet length will be 1, and it contained in an interval on which this function is going to be constant. Therefore, obviously, the Haar wavelet support is 0, 1, and this support is more than that. Definitely, it is going to be embedded in the new function. So, therefore, the inner product will become 0. For example, here I have given an example. See, this is an Haar wavelet. This is an Haar wavelet, and this is just I am considering let it be the new function wavelet. New function the length will be 0 to 2. So, this is defined in this way. Now, I am going to integrate minus infinity to infinity of this. 0 to half, this is going to be 1. This 0 to half, this is 1, and this is also 1. So therefore, this is 1 plus half to 1. This is minus 1, but this is again 1. So therefore, this is minus 1, and plus 0 to 2. There is no Haar function defined. So therefore, this 0 into this minus 1, this is going to be 0. After finally, you will get a 0 value. So that means in this way, we can say that whatever the Haar wavelet generated, it is the sequence is going to be forms orthonormal basis in the Hilbert space. So then psi is a wavelet. If I wanna define similar to Haar wavelet, if another wavelet, if I wanna calculate this orthonormality condition, it is very tough, right? For a simple function, we need to struggle more. But if I take some of the continuous function by framing by satisfying this wavelet property, if I wanna though create a sequence of function and which is going to be orthonormal basis for the Hilbert space, it is really a huge job. So that's why how to escape from this hurdle. So we can escape from this hurdle by using one more concept, that is multi-resolution analysis. So this will give information how we can create the orthonormal basis without using the manual representation. Whatever just we have done for each and every function, you need to calculate integration and it should be a 0. Then only I can say it is really huge job. So that's why this multi-resolution analysis yields how we can create orthonormal basis. Actually, the wavelet analysis says how to create an orthonormal basis in the respective domain and the respective space. So let's move to the multi-resolution. What it says? This multi-resolution analysis says is then introduced by the Malat and Mayer in the year of 1986. So here is the definition of multi-resolution analysis that says a multi-resolution analysis for Hilbert space consists of a sequence of closed subspaces, let's say Vj, in the Hilbert spaces, and the function phi belongs to V0 such that the following conditions holds. What is the first condition? The first condition says the each and whatever the space I have subspaces created, they are going to be nested. The V0 is embedded in V1, V1 is embedded in V2. Similarly, the negative the one also V minus 1 embedded in V0, V minus 2 embedded in V minus 1. Similarly, so on nested. If you take a union of all these subspaces and take a closure, that must be equal to your whole Hilbert space. Whole Hilbert space. And if you take an intersection of each and every space, it must be a trivial space. It must be a trivial space. Why it must be a trivial space? Because each and every are each V1, V2, V3, so on. They are all subspaces. Subspaces is with respect to identity, there should be a zero element with respect to additive identity. So therefore, if you take an intersection, it must be a zero. In every space, with respect to addition, the identity element will be element. So that's what the second condition says. And third condition says Vj plus 1 is must be same as the dilation, one-th dilation of Vj space. That means if I know the Vj space, immediately I can calculate what will be the space of Vj plus 1 by just taking a one dilation. And the Vj plus 2 taking a tooth dilation of Vj. Then every spaces, whatever the spaces I need, immediately I can generate by knowing that just one space. Let it be, if I know V0, I can generate V1, I can generate V2, similarly so on. So this is the third property says. And the fourth one says, if the any function belongs to one particular space, then if you take a, however the translation of that function, that should be present in the same space. That is the fourth one. And the fifth one says, whatever the translation you have taken, the TK of that phi must be from orthonormal basis of V0. So finally we are generated with respect to small subspace orthonormal basis. So if I know the orthonormal basis of V0, then I can extend to V1. Then if I know the orthonormal basis for the V1, then I can extend to V2, similarly so on. So therefore, for the entire whatever the closed subspaces we have opted from the Hilbert space, we can generate the respective orthonormal basis for each and every subspaces. This is the definition of multi-resolution analysis. That means in which way I can create the orthonormal basis. And here the lemma 1 says, whatever I just it is going to be repeating again. Lemma 1 says, if suppose in the multi-resolution analysis definition, if the third and fourth property satisfied in definition 3, then following property definitely hold. What is that formally property? If I know, already I told, if I know the V0, then immediately I can create V1, next V2, next V3. Similarly, in general, by knowing the V0 space, we can create how whatever the space subspaces we require, either Vj plus 1, similarly so on. That's what the first one says. And second one says, for this Vj, it is a subspace. That means there should be a basis. So this is going to be acts as a base for your Vj. So therefore, for knowing the V0 property, immediately we can extend for the entire whole space, Hilbert space. And next move, therefore, from this property, easily we can say that the R multi-resolution analysis, let's say psi is going to be defined in 0, 1, which is a characteristic function defined in the unit interval, and the Vj can be defined. So we any f belongs to your Hilbert space, those function is going to be constant in this interval. So therefore, the R satisfies this multi-resolution analysis. How? Here one example I have given. It is just R wavelet. Already I have defined in above. So this can be represented by the linear combination of scaling functions. So this is a scaling function. This is a psi. This is a chi. Is a scaling function defined in the 0 to 1 by 2 and minus 1 by 2 to 1. And this is can be represented by this way. And finally, by using the dilation parameter, this function can be represented 1 by root 2 times of this, similar 1 by root 2 times of this. So that is nothing but a linear combination of scaling function. If that means any form of any sort of the wavelet function can be represented as a linear combination by its scaling function. Now, phi is a scaling function and psi is a wavelet function. Here, let's move to the definition 4. Assume because I need to create a wavelet basis, still now I have created, just remember, still now I have created only orthonormal basis for scaling function, not wavelet function. Now I am going to create a wavelet function for orthonormal basis for the wavelet function. Now how we can create, let's say the definition 4 says the space Wj. I know already, by knowing V0, we can create V1, V2, similarly so on. Here I am creating for every Vj which are closed subspace of the Hilbert space, Then I am going to creating a one more space Wj, which is orthogonal complement of Wj with respect to Vj plus 1. So that is the Wj is an orthogonal complement of your Vj. That means if any function belongs to the Vj plus 1, then the inner product of f with respect to some of the function from Vj must be 0. Then only Wj will become orthogonal complement to Vj. In this way, another way of this definition says, that means the Vj plus 1 is a, whatever the functions present in Vj plus 1 are either function of your Wj or a function of Vj. That is, Vj plus 1 can be represented as a direct sum of Wj and Vj. So this is the another way we can say how the direct sum perpendicular subspaces are going to be generated. Here one more lemma I am considering here. Assume that the function phi belongs to Hilbert space, which generates multi-resolution analysis. Let's psi is belongs to that same space. Suppose this Tk psi is an orthonormal basis for W naught, then the first one, this is going to be orthonormal basis for your Wj in the same way of the scaling function. In the same way, the scaling function has been generated, right? If I know the orthonormal basis for the V naught, then I can create a orthonormal basis for the V1 by taking a 1th dilation, d power 1. Similarly, for the wavelet function also, if the W naught I have a orthonormal basis, then obviously for the Wj, this will act as a orthonormal basis. And the function dj tk psi, where j and k belongs to your z, forms orthonormal basis for your entire Hilbert space L2 of R. So therefore, the psi, by the definition of wavelet, the psi will become a wavelet, right? So that means from the V naught, we have created a W naught. If I know the W naught orthonormal basis, easily I can find for any Wj orthonormal basis. Now take an union of orthonormal basis of Wj, that is nothing but orthonormal basis of your Hilbert space. And the third one says this is an orthonormal basis for your V naught, and this is orthonormal basis for apart from your V naught, it again forms a orthonormal basis. Again, as usual from the previous definition. Previous definitions. This is the one of the way we can create the orthonormal basis for your wavelet function. And here another way we can say that, let's see the lemma 3. If any function satisfies the scaling equation, that function will become a scaling function. That's what lemma 3 says. Assume that the function phi is in Hilbert space, generates the multi-resolution analysis. So that is it already scaling function. Then if it is a scaling function, then there is a one periodic function h naught such that the phi cap of 2 nu is equal to h naught nu phi cap of nu, where nu is any real belongs to your R. So that means if this property satisfies equation 1 satisfies, then this phi function, then this phi function will become a scaling function, and this h naught will become a one periodic function. With respect to using this one periodic function, then I can say the psi is going to be scaling function in presenting in Hilbert space. So here proof is there, but proof is not necessary. So just I am using this equation 1 to create a orthonormal basis for a wavelet function. So now this is the proof. I am not just emphasizing more on your proof. This equation here, equation 1 is called as the scaling equation, and the function phi satisfies the scaling equation is called a scaling function. And this lemma says that necessary condition for the for a function of phi to generate a multi-resolution analysis is that phi is a scaling function. Now move by using this because it is a scaling function. Obviously, there will be a one periodic function h naught. By using this one periodic function, we are going to create a wavelet function. As of now, I am in the I am on only scaling function. Now I am switch over into the wavelet functions. How? Let's see here. The theorem 1 says the wavelet orthonormal basis. This theorem says how the orthonormal wavelet is going to be generated. They assume that the phi is from Hilbert space, so which is generated by the multiple analysis. That means what? Already with respect to phi, there is a orthonormal basis. By taking union of all orthonormal basis for the V1, V2, V3, so on, it will become an orthonormal basis for the Hilbert spaces. Next, and H0, since phi is an this scaling function, therefore H0 is going to be inevitably generated from previous lemma. So that is one periodic function is going to be generated. Then by using H0, I am going to define a one periodic function. Let it be H1. So H1 is defined in this way. Also define the psi by using this concept. Here I know what is psi and I know what is H1 of V, H1 of nu. So then easily I can find the psi cap of 2 nu. Then this Tk of psi will become an orthonormal basis of W0. W0, just you carefully just see here. Till now I have considered only the scaling function, and with respect to scaling function, one periodic function H0. With respect to that, we have created a H1. By using H1 and scaling function, we have created a psi cap of 2 nu. From that, the psi has been defined. So for psi, the Tk of psi is going to be orthonormal basis for W0. Then by using the dilation parameter, if suppose j is equal to 1, then it is orthonormal basis for your W1. Similarly, for every value of the j, then this will become orthonormal basis for your Hilbert space. That is, the psi is wavelet. So this is the way how we can create the wavelet. And here this definition phi says phi is from the Hilbert space, and Vj is going to be defined by the span of this space, and it will be denoted by the orthogonal projection in your Hilbert space onto Vj by the Pj. That is, the Pj is going to be orthogonal projection. And here one more data, because previously I told Vj plus 1 can be written as a direct sum of the Vj and Wj, because whatever the element belongs to your Vj, they are not an element of your Wj, because they are the perpendicular spaces. So therefore, by the direct sum definition, we can directly represent each and every Vj plus is a direct sum of Vj and Wj. And here one more dilemma I am considering. Why means to say the property of the your wavelet. Suppose that the scaling function phi, the psi is going to be bounded support, then the following property inevitably holds. What is that? The first, if it is scaling function, just carefully listen. In upcoming theorems, I am going to using this statement. The scaling function phi has bounded support. Then first one, the only finite number of scaling coefficients are non-zero. If you approximate any function by the orthonormal basis of your phi, then those coefficients, the scaling coefficients, the finite number of scaling coefficients are non-zero. Infinite number of scaling functions, scaling coefficients are going to be 0. That's what the meaning of first statement. And the second one says the corresponding wavelet. If the psi is a scaling function, obviously we can create by above theorems corresponding wavelet psi constructed according to MRA as also bounded support. If the phi has a bounded support, a created wavelet also having a bounded support. If a phi is k times continuous differentiable function, then the psi is also k times continuously differentiable function. Those are the properties inevitably satisfies and carried forwarded by the scaling function. Now move to the properties. Since in the beginning told I have opting wavelet methods. Why? Because it has some of the beautiful properties. What are those properties? Here one is vanishing moment. What it does actually, vanishing moment. Here you see the purpose of this section is to discuss the properties of the wavelets. And assume if the any function phi belongs to your Hilbert space, obviously here I have considered the f belongs to your Hilbert space, definitely it can be written as a linear combination of basis functions. But here those are the basis function of your Hilbert space. So that means f can be written as a linear combination of all those basis functions. That's what written in equation number 2. Now all information of the about f is stored in the coefficients. Where is the coefficient? These are the coefficients. These are the coefficients. So therefore, now I need to calculate. I need to find the entire f. So therefore, I need to calculate each and every values of your coefficient. But previously, just now in the previous lemma, I told that if the psi is belongs to Hilbert space, which is having a orthonormal basis, then obviously whatever the function approximated by that having a coefficients are finite number of non-zero coefficients. So therefore, in the first series term, there is no problem. By above lemma, it will become the finite number of coefficients will become a non-zero. That means infinite number of coefficients will become a zero. So therefore, from the first term, I get only finite number of terms. The problem with second one, that theorem says only on the scaling function, not on wavelet function. But it is the second term, it says about the wavelet function, wavelet coefficients. So therefore, how I can reduce these infinite number of coefficients? For that, I am going to use the threshold property. Here is the threshold concept. So this is the sequence. From this infinite number of coefficients, I am going to choose only dominating coefficients. So by using that thresholding property, so here for epsilon greater than 0, we keep only the coefficient in 3 for which satisfies this condition. Whatever the value, the absolute value of the inner product of this is greater than or equal to epsilon r, I keep only that coefficients and remaining coefficient I am going to neglecting because these are going to be dominating. Whatever the dominating and remaining undominating coefficients, I am going to suppress. I am neglecting that. So for that, I am using this theorem. This theorem says, if suppose Ek is orthonormal basis in the Hilbert space H, then this sequence is going to be converged. This sequence is going to be converged if and only if this unknown coefficient sequence belongs to L2 of n. So this says the coefficient is belongs to L2. Thus, the only a finite number of indices j, k belongs to your the cross product of z will satisfy equation number 4. A key feature of this wavelet theory is that often is possible to choose the wavelet psi such that many of the coefficients in this sequence are small with relevant to the signal whatever the function we have chosen f. That is, a relatively small number of the quotient will satisfy the equation number 4. Therefore, huge number of coefficient is going to be nullified. So by using this threshold property, so then easily I can represent entire function by using the only few number of coefficients. So here is the definition of vanishing moments, and here the R wavelet has only one vanishing moment. If the psi having a more vanishing moment, then the respective coefficient, whatever the approximated series representation, whatever the unknown coefficient presented, those will be more number of coefficient will be neglected. So therefore, here to justification this sentence, I am saying this theorem 4. That means decay of the wavelet coefficient. What it says? So here assume that the psi is from your Hilbert space and is compactly supported as n vanishing moments. Then for any n times of differentiable function f belongs to your Hilbert space for which nth derivative fn is bounded, then there exists C such that satisfying equation number 5. That means when j into n tends to more number of vanishing moments, j into n tends to infinity, this is going to be approaches towards to 0. So that means which is less than epsilon. But here I told that this is going to be only dominating coefficients which must be greater than or equal to your epsilon. So therefore, the many number of coefficients is going to be neglected from this equation number 5. So this is the one of the beautiful property of your vanishing moment. And next, one more beautiful property, that is the orthonormality. So for the orthonormality, you see why we use this orthonormality as a tremendous application, because you see S is this, that means one set of orthonormal basis for the Euclidean space, let it be U. Orthonormal basis means if suppose any vector V belongs to U, then obviously that can be written as a linear combination of this. But C1, C2 are the unknowns. Easily we can calculate by using this operation without taking a linear combination. So directly we can say that what will be the respective coefficients. And here one more theorem says that if x1, x2 and so on are the sequence of linear independent vectors, by using that I am going to creating the orthonormal vectors, then the space generated by this orthonormal vectors and this linearly independent vectors must be same. Both are acts as a basis. That means either it is a finite or infinite number of elements, vectors, the respective spaces are same. But whatever the vital role played by the basis element, orthonormal basis element and this just linearly independent vector are quite different. Why they are quite different? Here is one example. I have considered a polynomial space which is a polynomial space, let it be A is a polynomial space and orthonormal basis is this. This is just orthonormal basis. Sorry, this is normal basis and these are the orthonormal basis. Then I choose one element from your polynomial space, let it be 1 plus 2x plus x square. I need to approximate by this given basis. So I need to approximate. So this is the first. I am approximating by the just linearly independent vector. That is 1 plus 2x can be written as a linear combination of these just basis elements, and expanding this and calculating all a1, a2, a1, a, b, c, and finally I get a ABC, and that to substituting this equation I will get the 1 plus 2x plus x square is same as same, right? This is the procedure. If I wanna choose just basis element. If I choose orthonormal basis, then I am not going to express in the linear combination. Just I express by using this concept. That means A can be calculated by taking inner product of this. That means this is the polynomial which I am going to approximate it, and this is the first this basis element, and calculate this. I will get a what is the value of E. Similarly B and similarly C. Substitute and you will get exact approximation. See how simple. If I use the orthonormal basis, this is the simplicity I am going to get it. Because if I use just basis, it is time consuming. So that's why while you using the program, if you use orthonormal basis, you get that means a solution may you get same, but the time will be reduced if you use orthonormal basis. And one more advantage is if A4 doesn't belong to A, because A containing only polynomial of degree 3 but not 4. Then by using the basis I cannot express this x power 4, but by using the orthonormal basis I can fully express that as a linear combination of your x power 4. So here I have taken this one example. For different value of x, I have approximated the x power 4 by using the orthonormal basis. Here is so 10 power minus 2. First two digits are going to be matching with the x power 4. So therefore, this is an advantage of orthonormality of the wavelets. And one more property, compactly support. The compactly support says if any function f we call as a set which is x belongs to your R, where the f is not equal to 0, is going to be support of your function f. Actually, the support means which is a closed, the smallest closed set containing the points where the function is non-zero. So that is a closure of domain is a compact set. So with these property, the wavelets plays a vital role while solving in the partial differential any sort of the equations. So here I have considered one of the polynomial wavelet which is defined in reference 2 and 3. Due to lack of time, I am just skipping this. I am just considering whatever the wavelet they have defined. So here is the wavelet they have defined. So this is the wavelet I am going to considering in my wavelet method. So this wavelet, now I create operation matrix of integration. This is the wavelet. I use this as a collocation points to create operation matrix method by choosing different values of j and l and capital J. I form the operation matrix. Let it be this is a H. For every function, I am applying the collocation point. They are representing the first wavelet function in first row, second function, similarly so on. And this is the first operation. This is just a wavelet representation in the matrix form. Now I integrate minus 1 to x psi j comma l of x. Then I get again a function of x. For the same collocation technique, I apply here. Then I get one more matrix. This matrix H prime is the first operation matrix of integration. Once again I integrate. I get a one more function G, J, comma L. Same, I apply the collocation method, collocation points. I will get a H double dash. So for simplification, in particular, I have given a J is equal to 0 and 1. Then the respective matrices are H, H prime, and H double prime. These are the two matrices which is 3 by 3. Now I am going to apply this matrix to solve this our new model. Here you see, this is the model I have considered. Actually, this is generated by us. New model, the romantic and interpersonal relationship model. Actually, why we have considered this model? Because you see, nowadays the social, the health is depend on whatever the family health. If the one place 100 family health and live with love and prosperity, then obviously that the entire surroundings, entire area will be finer and healthier. So based on this concept, we have generated this model. That means how the love and affection within the family will affect the social, our society health. Here I have considered this romantic and interpersonal relationship model comprises 4 dependent variables. So one is love of male. Here I am not considering the population. I am considering the love of male, love of female, and love of children, and love of society. So and similarly, the love of male depends on the ovulation rate of the male encouraged by the others, and this work stress and the financial status of the male, and similarly female and the children. For the children, love of the children will depend upon how the parents will take care of the children. So that is directly proportional to how the children are going to be love their parents. Similarly, the same properties I am going to be extending for the for the society. How the society will love your family. So that means how they respect your family. So that is the equation 11 says. Here DM says the rate of change of the love of male is depend on the gamma 1 says that how much obligation rate of 1 is encouraged to others. So that means why I am giving my negative notion. So because if I does some of the work to some of the my friend, if he forget whatever I have helped him, if he forget my work, then obviously I will hate him. That means my love on him goes on reduces. So that's why the negative notion I represented there. And the gamma phi represents a rate of 1 is encouraged their helpful activities. So if suppose I help to my spouse, if suppose my spouse or my wife immediately given appreciate my work, immediately so my love will increase, or my taking care he will increase with respect to her, right? So that's why it is a positive notion. And the C1 represents the rate of attraction towards. So that is, it is a positive. And D1 represents a rate of financial status. If my financial status is better, then I love family, my love on my family will be higher. If my financial status is not as much with desire, then definitely I won't concentrate on my family, right? So therefore, the D1 represents my financial status, and the E1 represents the rate of work stress. If I have a more work stress, then obviously my love on my family will be reduced. If the work stress is less, then automatically I can take care of my family well. So therefore, I am represented by negative E1. And similarly, the F1 represents, the romantic intimacy with their male romantic intimacy with female. So therefore, obviously, the love will be increased. So therefore, I represent it as a positive F1. So in such a way that the rate of change of love of the male goes on vary, depend upon these parameters. Similarly, the rate of change of female is also varied, and rate of change of child is also goes on vary. Each and every depend on each and every parameters, and the rate of change of giving a respect of your society is also vary on each and every parameters what I have defined in equation number 11. Now let's move. How our method will yield a better result for varying each and every parameters given in equation number 11. And here is the method. Here method I have considered. This is the method I have considered by using the two techniques. One, if you see when you are approximating by the any polynomial or wavelet functions, if you increase the collocation points, then also accuracy will be increased. Or else, if you increase the number of terms taken by the wavelet basis function, then also accuracy will be increased. But here, still now in the literature we can see that only either out of these two techniques, any one technique has been utilized. But here I used both techniques. That means even I increased the collocation point and number of terms also increased. So therefore, I used the Riemann integration concept. That means I partition the interval. Actually, this is a whole interval. This interval I partition as a bk, which is the union of these subintervals are going to be this entire large interval. So equation number 12 represents my approximation. This represents rate of change. Here I have considered the four variables. In general, I am defining, let's say, I, k prime, the rate of change of male, love of male, female, similarly children and society. This is approximated by this. This is my wavelet function defined in above, and this is the unknown coefficients. And here, entire this term I represented by the capital Q. This equation 3 represents simple representation of equation number 12. So that is, the Q is a matrix representation of the unknown coefficient. Similarly, this phi is a matrix representation of the your wavelet function. And here I have considered the this characteristic function, delta of xi is a characteristic function, where the xi is an element of your bk, which is a partition interval, then it is going to be 1. If it is doesn't belongs to bk, then it is 0. Therefore, by using this characteristic function, again I am approximated z I prime of xi is equal to this. Now I collocate this by using this collocation point in each and every subintervals. Then I get equation number 14. The 14 can be represented by equation 15 by representing the matrix representation. So matrix representation here, this is going to be matrix because H I have defined rare in previous representation operation matrix of integration. Therefore, LKB is nothing but your H. Here for my notion, I have represented by LBK to represent in subintervals. In which intervals I am going to approximate. So that's why I represented LBK prime. So equation number 16, which is nothing but Z of Zi of your respective collocation points. Now substitute 14 and 16 in the given model. Then it will yield a system of non-linear algebraic equations, and solving those algebraic equations by Newton-Raphson method, then I get an unknown coefficient values and substitute in equation number 16, finally it will give numerical wavelet based numerical representation of our considered model. Here is the some results. These are the parameters I have assumed to solve the respective considered model, and here you can see. So this is this model is new. It has no exact solution. So that's why I compared those relation. LWCM means because that polynomial, whatever the wavelet function defined using the Legendre formula. So that's why I call that as a L polynomial wavelet collocation method. That's what represents here. And here compared with the RK4 and ND solver, this is absolute error. This is RK4 method and ND solver method absolute error but this is our method absolute error. That means it is more closer to your 0. So therefore, we can say that this is actually j is equal to 3, not k is equal to 1. This says our method will yield better accuracy than your RK4. Similarly, this is for female love, same structure we are going to observe here, and this is for the C and this is for S. And this is a graphical representation how our solution is closer to ND solver and RK4 method. Similarly, this is for C and this is for S. Now the parameter vary. Just you see the variation of reaction, that means the gamma phi I vary Gamma 5 means what? The reaction rate of one is encouraged to other helpful. So that means if I help to my wife, then if my wife is appreciated my work, then obviously my caring and love is going to be increased. So therefore, when delta 5 is increased, then obviously here you can see that the love of the male is also goes on increases. When the love of the male goes on increases, the family will be healthier and with with love and affection. Therefore, that respective family will not harm or will not think bad on the society. So therefore, on the society also, the love is going to be increased. So if you don't harm the society, society also will not harm. Society is nothing but your neighbors, right? So will never harms you. So this is directly proportional. So how the male love leads to the healthier society. Similarly, for the next one, it is similar to the female also. The same structure we are going to observe here, the same physical variation. And here is a financial status of D1, financial status of the male. The D1 represents financial status. When the male financial status is increased, that means increase means whatever he wants, he can take care. So therefore, whatever he wants, he can purchase. Obviously, he can take care of his family, whatever they require. So therefore, the family love is also increases. So therefore, love of the child is also going to be increased. So therefore, if both are increased, the family will be healthier. And so therefore, the respective society is also, love of the society is also goes on increases. So, and the next one, similarly, the same structure we can see with respect to the financial status of the female, and it is a romantic intimacy. If more romantic intimacy, the bond will be increased. So therefore, the love is going to be increased for male and female. Similarly, the society is also the healthier. So with respect to this, this is the new model we considered by this wavelet technique to analyze these results. So obviously, this nature will be valid with our society. So therefore, immediately we can accept this our technique is yielding a better results for to analyze the many different mathematical models. So this is our presentation. In the conclusion part, so here we have learned how the orthonormal basis has been going to be created by using the theorems by the one periodic function H naught and one periodic function capital H1 for the for the wavelet basis, and the way of creation of operational matrix of integration, and the method by using the both increasing the terms and the collocation technique. And here considered model is also well justified with the considered method. So therefore, freely we can apply by using the different wavelets, or else we can create different wavelets by using this concept. We can extend our research work. So thank you.
Thank you very much, sir.
Hello.
Thank you very much, sir, for presenting wavelet analysis and its applications. Yes. Any questions from audience?
Sir, can you explain more about multi-resolution analysis? Sir?
available, sir. Sir, once again, thank you for your presentation. Okay, sir. Mathematical Society and life member Punjab Academy of Science and life member Indian Society of Industrial and Applied Mathematics, annual member of Society of Industrial and Applied Mathematics. Madam has guided Madam has guided
Sir, you are
five
not audible.
PhD students and she has given a talk in a national, international conferences. Okay. With this brief introduction, I welcome Madam for the presentation.
ಯಾರು ಸರ್ ಇದು ನೋಡ್ರಿಪ್ಪ ಆಯ್ತಾ ಸ್ಲೈಡ್ಸ್ ಆಗ್ಯಾರ Madam ji, very good evening.
Good evening, sir.
Madam, you have accepted our invitation and graced this occasion, grand success, and you are a very brilliant academician. We are lucky to have such a great academician with us. Madam, I heartily welcome to deliver your talk. Please start the talk, madam.
Thank you, sir. Thank you so much. First of all, I would like to thank Professor S.P. Sharala Shetty, who has invited me to deliver my talk. My topic is study of nonlinear reaction diffusion equations using quintic Hermite splines. These are the main contents. I'll start with introduction, then I will give a brief introduction of Hermite splines and their application, and then we will discuss about the stability and the convergence of these splines, and then move on to apply these Hermite splines on the reaction diffusion equations, and then I'll conclude my lecture. So we'll start with the introduction. Reaction diffusion equations represent the change in substance over space and time due to diffusion. It represents the system of equations combining the reaction and diffusion terms. These equations are used to model the systems in fluid dynamics, oceanography, aerospace engineering, etc., and can be represented in both linear and nonlinear forms. The simple nonlinear reaction diffusion equation is Berger equation. Berger equation was first introduced by Bateman in 1915 and in his famous article on motion of fluids. And then Berger has studied this equation in his aerospace engineering and named it as Berger's equation. After Berger, Langerstrom has studied the general solution of Berger equation in theory of viscous compressible fluids. But the most famous solution which we use till today to compare our results was given by Hope and Cole separately, and this solution is generally known as Hope-Cole transformation. The Berger equation is similar to Navier-Stokes equation, which is again a reaction diffusion equation and has originated from the physical applications from fluid dynamics such as compressible fluids having small viscosity or heat conductivity. This nonlinear homogeneous parabolic transient equation has wide application in aerodynamics, shock wave theory, in real fluid turbulence, and in continuous stochastic processes. The other examples of nonlinear reaction diffusion equations are generalized Berger-Huxley equation, generalized Berger-Fisher equation, Newell-Whitehead equation, Pizzo-Nagumo equation, damped Berger equation, heat conduction equation, And if we go for higher order, then we have Krumator-Shevensky, Fischer-Kolmogorov, Fischer equation, etc. These are all reaction diffusion equations. The general form of reaction diffusion equation over the domain AB into 0t, where AB is the domain in spatial direction and 0t in time direction, is this one, where epsilon is the perturbation parameter and beta is any non-zero, any parameter. It may be 0 and may be non-zero. F of u as the source function or the source term. This function may be linear or non-linear. U raised to power delta curl u by curl x represents the advection term, and curl square u upon curl x square is our diffusion term. And I have taken the Dirichlet boundary conditions to study my problem. However, we can take Newman's or standard mixed equations, mixed boundary conditions too. The initial condition for the function is taken to be this represented by equation number 2. Sorry, this is misprinting 0, 1. The x domain is AB, not 0, 1. Now we come to the application of quintic-Hermite splines. Quintic-Hermite collocation is one of the weighted residual methods which is followed to solve the reaction to solve the nonlinear partial differential equations in a convenient way. This is a combination of orthogonal collocation method and Hermite splines. As I am discussing about quintic-Hermite splines, so we are talking about quintic-Hermite. However, we can use cubic, septic, sextic splines also. But why the application of cubic Hermite and quintic Hermite is higher than the sextic or septic splines, that I will tell you at the end of the application of these splines. The unknown function is approximated by a trial function which is assumed to be a series of quintic Hermite interpolating polynomials. The boundary conditions are satisfied by the appropriate choice of constants. The reason being, as the quintic-Hermite splines interpolate the function as well as its first and second order derivatives, therefore the boundary conditions are also interpolated in quintic-Hermite in the Hermite splines, whatever we take. However, this is not possible in case of these splines. There we have to adjust the boundary conditions. So in case we apply the Hermite splines, we follow usually interior collocation. Now, Hermite interpolating polynomials are the generalization of the Lagrangian interpolating polynomials, but unlike Lagrangian interpolating polynomials, these polynomials of order 2k plus 1 and interpolate the function as well as k successive derivatives. Therefore, for cubic Hermite splines, k is 1, and for quintic Hermite splines, k is equal to 2, and so on. As I have discussed earlier, we are talking about, in this lecture I will discuss about quintic Hermite splines. So I have taken the quintic Hermite interpolating polynomials as the base functions which interpolate the function as well as its two consecutive derivatives. As these polynomials are quintic in nature, therefore each polynomial is of degree 5. And there are total 6 polynomials which interpolate the function and its two consecutive derivatives at the point xi and xi minus 1. This is the structure of quintic Hermite splines. We have 3 types of splines such as Pj, Qj and Rj. All these are defined on the interval xi to xi plus 1, xi minus 1 to xi. This is the structure of these Hermite splines. Now to apply the quintic Hermite splines on a differential equation, we approximate the function u in terms of p, q and r. And to apply the orthogonal collocation within each subdomain of xi to xi plus 1 or xi minus 1 to xi, we introduce a new variable xi such that the step size or the length of each subinterval is hi. As we are discussing the uniform partitioning of the subdomains, therefore HI will be equal to H in the next slides. Because we are discussing the uniform partitioning, not the non-uniform partitioning. So as x varies from xi minus 1 to xi varies from 0 to 1. So by making this transformation, the quintic Hermite splines mentioned here, Pj, Qj and Rj, converts into these 6 Hermite splines of H1, H2, H3, H4, H5 and H6. Now at xi equals to 0, you can see H1 is non-zero and all other are 0. At xi equals to 1, H2 is non-zero. Similarly, when we take the derivative, H3 is non-zero at xi equals to 0 and H4 is non-zero at xi equal to 1. Similarly, H5 is double derivative, we take double derivative, H5 is non-zero at xi equals to 0 and H6 is non-zero at xi equal to 1. So this will help to interpolate the function and its two consecutive derivatives. To implement these Hermite splines over the domain, we have this type of structure. So this will help us to assume that the functions are continuous at the node points. So there is no need to assume another or additional condition that the function is continuous at the node points, as these Hermite splines have inbuilt continuity. So we don't need to add another condition which reduces the number of equations and hence the computational time and the metric structure. As unlike in Lagrangian interpolation polynomial, because if we apply Lagrangian interpolating polynomials on the finite elements, we have to impose another condition that the function and its first derivative are continuous at the node points. This increases two more equations within each subdomain. Now this is the approximation of function u in the gamma domain. This gamma represents the number of subdomains. Hj xi represents the Hermite splines and uj gamma is the undetermined coefficients that we have to determine. Now we come for stability and convergence analysis. To discretize the non-linear reaction diffusion equation in time direction, we have proposed Crank-Nicolson finite difference scheme. Crank-Nicolson finite difference scheme is proposed reason because of its rate of convergence, as it has quadratic rate of convergence, that is of order delta t square. It takes the mean of the iterations in spatial direction. So we have applied this Crank-Nicolson scheme in this form. Now the next step is to linearize the non-linear term, that is the function which is iterated at n plus 1th and nth iteration, and the non-linear term u raised to power delta into curl u by curl x, which is iterated at n plus 1th and nth iteration. To quasi-linearize these two terms, these two non-linear terms, we use the method given by Rubin and Graves and the Taylor series approximation of multivariables to quasi-linearize these two non-linear terms at n plus 1th iteration. After implementing the quintic Hermite approximation, these equations can be written in this form. This is the equation at pth collocation point. Now we will discuss now the point is how many collocation points we take within each subdomain. In case of quintic Hermite splines, we take 4 collocation points within each subdomain, because the remaining 2 points are 0 and 1 being the boundaries. So within each subdomain, 4 collocation points are introduced. These collocation points are usually taken to be the zeros of any orthogonal polynomial. We have taken the zeros of Legendre polynomial, but you can take, the zeros of Chebyshev polynomial can also be used as coefficient points. Now we come to the stability of the proposed scheme. The stability of the proposed scheme is discussed using von Neumann method. To implement the von Neumann method, the nonlinear term of curl u by curl x is taken, is quasi-linearized by taking its maximum as kappa for all the points in the domain. Now, if we take u raised to power delta into curl u by curl x is kappa, we have applied this technique on the Berger equation for delta equals to 1. So, when we applied it on Berger's equation for delta equals to 1 with no source term, maximum of curl u by curl x is kappa. Now, to implement the von Neumann scheme, the coefficients ujn, we can take it, we have taken it here as ajn, is to be eta raised to power n exponential iota j h gamma. H gamma is just to simplify within each subgamma subdomain, otherwise it is h into zeta. Zeta is the mode number, and after simplifying we get this form of equation. Now n plus 1th iterations are on left hand side and nth iterations are on right hand side. And on simplifying, we get this form of eta. Now, if mod of eta is less than equal to 1, then the proposed scheme is unconditionally stable. And in this case, mod eta is less than equal to 1. So, therefore, this technique is unconditionally stable. Now, to discuss the convergence of the proposed scheme, we have chosen the method of eigenvalues can also be used, in which all the eigenvalues lies in the left of the plane. Then we have to discuss the existence of the solution, the maximum principle proposed by Miller, Riordan and Shiskin has been discussed. And then our next theorem is the function u of equation 1 defined on the domain omega, there exists a constant c. That means the function should be bounded over the domain, that should be uniformly bounded. Then the solution will exist. Then the quintic Hermite splines are bounded over the domain by the unity, and the solution with respect to t exists if and only if the first order derivative is bounded over the domain omega. Then the convergence of these splines depend upon the difference between exact and numerical solution is less than equal to is of order h raised to power 6 minus j. As we have second order derivative, therefore quintic Hermite splines are convergent of order h raised to power 4. Then we have application, and if we combine that the global error estimate for time direction and for this Hermite spline or spatial direction, we find that, sorry, this is delta, this is not delta t, this is delta t square. The global error estimate for the quintic Hermite splines for the function u in temporal and spatial direction is of order delta t square plus h raised to power 4. This is delta t square plus h raised to power 4. Then we have the application part. Application to the numerical problems. First we applied it on the Berger equation for delta equal to 1 with no source term or zero source term. The boundary conditions are taken to be the Dirichlet. with initial condition is taken to be sin pi x. The solution is given by hot and cold. The initial condition is taken to be sin pi x. And when we compare the results with the exact solution, we found that the proposed method gives better results than the results given by other, than the results proved or introduced by using other techniques, that is differential quadrature method, collocation method, etc. These splines, 20 Hermite splines gives better results, and these are computationally efficient and easy to implement, because in 20 Hermite splines we need not to introduce any fictitious nodes to satisfy the boundary conditions, as it already interpolate the boundary conditions. Then we compared the result for the value of epsilon 0.01, and again found that the proposed method gives better result as compared to already existing. Then we have compared the results for different values of epsilon. Then we check the results graphically at different time levels, starting from small time to higher time, that is from 0 to 1, and we found that 20 Hermite splines are more smooth to interpolate the function u as compared to other one, and similarly the 3D projection of the solution also represent the same thing, that the solution values are smooth enough to be presented. Similarly, the behavior of solution profiles is shown for different values of epsilon at different time levels. Either it is smaller one or larger one, the behavior of solution profiles is smooth and is not fluctuating at any time level. This is the contour graph which is shown for epsilon equals to 0.03. Then the next problem is solved for the initial condition 4x into 1 minus x. The boundary conditions are taken to be homogeneous Dirichlet boundary conditions. Here again we have compared the results for epsilon equals to 0.1. The values are found to be better than the existing values. And in this table we have compared the results for epsilon equals to 0.01. And in this table we have compared the results for different values of epsilon with the values already given in the literature. And this is the graphical behavior which is shown at different time intervals, which shows that whether the time is small or large, the values are not oscillating at any point and converging smoothly. This is the contour behavior. This is the contour behavior for epsilon equals to 0.05. Then the next equation is Fisher's equation, and in this equation the source term is non-linear and is taken to be alpha u into 1 minus u. Here the advection term is taken to be 0 and epsilon is taken to be 1. Therefore, the initial and boundary conditions are extracted from the exact solution. The partitions and space direction are taken to be 50. So, there will be total number of points that is to be interpolated at 200. The time number, the delta t of step size in time direction is taken to be 10 raised to power minus 5. The alpha in this equation is taken to be 10 raised to power 3 and 10 raised to power 4. That is in source term. The source term is taken to be at higher level. And this is the behavior of solution at small time period, that is from 0 to 2 into 10 raised to power minus 3 for alpha equals to 10 raised to power 4.